Hi to my follower that don't follow me. So we will unpack this title during my presentation, which is there are several components. So let's start with the climate change. Climate change is probably the greatest challenge of our time. We are all concerned about it. And its effects are ubiquitous, from prolonged period of drought to very intense rain, to thunderstorm, to fires in areas that never experienced it before. Just a sad example from my country, Italy. In the beginning of May, in the northeast of Italy, it rained the same amount. In 48 hours, it rained the same amount of rain that it usually rains in 4 months. That's led to floods and several problems. So this is the greatest challenge of our time. It's a great concern. And multiple strategies and approaches have been proposed to mitigate climate change, not to fight, but to try to mitigate, to reduce it. We go from, it's a huge spectrum. We go to reduce the use of fossil fuels, improve renewable energy, electric car, but even personal variation, change in our life, like a dietary variation, like reducing meat consumption. What all these solutions share in common is reducing the greenhouse gases emission. And among greenhouse gases emission, the most important one is CO2. So all these strategies have in common the idea of reducing the amount of emission. And as a part of this global effort to mitigate climate change, one solution that has been proposed is the geological capture and storage of CO2. So for most of you, this is probably a novelty, but CO2 can be captured from the atmosphere and pumped and stored in the subsurface. So this is basically the idea. Here we have a scheme that can help us to understand. Basically, we have a source that's producing CO2. For example, in this graph is a cement manufacturing plant, cement, which is one of the greatest in an industry that produces a lot of CO2. The CO2 is captured, and then it's pumped in the subsurface through some holes, drilling some holes. We can reuse existing holes, or we can create new holes. So this is the idea, and potentially the CO2 should be stored there for as much time as possible. So it's the opposite of what we do with fossil fuels. With fossil fuels, what we do, we extract from the subsurface and then we use it. Here we are doing the opposite. So one of the ideas is also to use expired, let's say, fossil oil and gas fields. But of course, we can't blindly drill and pump CO2. We need to know where. And if a place, if the subsurface we're interested in can get CO2. For example, we are interested in knowing if enough CO2 can be stored. But most importantly, if this is not going to impact somehow, for example, producing earthquake, producing some fracture in the subsurface. And even most important, we need to know if the CO2 is not going to leak and go again into the atmosphere. So we need to really well characterize the subsurface we are dealing with. So we really need to know all the properties of the subsurface. And two of the properties I'm interested into, and I'm going to talk with you, are permeability and cementation. These are two properties of rocks and of soil that are really important in this situation. So let's talk about permeability. We all have a basic intuition of the concept of permeability. Even in social science, it's used that the society is permeable to certain ideas. It means how easy a medium can be, something can flow through a medium. And in the context of geology, of soil and rocks, it means how easily a fluid can flow through a rock. Here we have an example. On the left, we have a more permeable material. On the right, a less permeable material. And as you can see, in the more permeable material, the water flows more easily. There are more spaces, and it's easy for a water to flow. But you can imagine also CO2 flowing. It's the same idea. So we are interested in rocks to be permeable enough to host and to store CO2. So this is the first properties we're interested in. The second property is the cementation. Cementation is less intuitive. The word, it sounds familiar, but it's less intuitive. The cementation is the process by which particles, like imagine sand grains, the one you find on shore, are compacted and then are bound together to form a rock, sandstone, a rock that you find a lot also in Israel, in the Negev, and in the Dead Sea area. So basically, this process is really important because it's influenced the strength of a rock. You can imagine if you are going to drill and pump something in the subsurface, we need to be sure that the rock are strong enough, hard enough, and also it influences the permeability. So basically how it works, this is a really, imagine these kind of balls are grains, like the grains of sand, and in between there is water. And with time, these grains can be compacted for pressure because they are buried in the subsurface. And at some point, there could be some precipitation of minerals that link to grains. And this creates a rock. This makes a rock, like unconsolidated grains, to become a rock. And this, of course, is going to influence strength and permeability of a rock. So what's the point? What's the state of the art? Today, the determination of these two parameters is very time-consuming and costly, because permeability, you need, to estimate permeability, we need to have sample of rocks and send it to labs. And as those of you deal with lab measurements, it's very expensive, time-consuming. Not everywhere you have the same instrument. So sometimes you need to send a sample to another lab. It can be really complicated. While cementation, for cementation, we need to analyze various images of rocks with microscope. And that's also really complicated because you need a great expertise and a lot of time. So what's the idea? The idea is, can we use artificial intelligence to speed up and automate the procedure of estimating this kind of properties of rocks? And I'm going to focus mostly now on what I did on the cementation estimation. So first, let's introduce a little bit AI. AI is ubiquitous. We all know now ChatGPT, we all play with it. And that's natural language processing. But another field where artificial intelligence demonstrated very effective is image analysis. Automatic image analysis, image classification, how it works. The idea is this: you have an input images of something, then you send these images to an algorithm, and this algorithm output what we call in technical jargon segmented images, an image divided in its components. So here you have a bicycle in green, the background, and the person who is driving. So the output, the algorithm understands which are the components of the images, and it segments the images in different components. This is used in a lot of fields. One is self-driving cars. So the cars basically has images of what is ahead of it, and segments, understand if there is a road, if there is a car, if there is a person, and decide which is the next move. So the idea is, can we use this kind of technology to analyze rock images in order to determine cementation, and from that also answering other questions? So basically my project, my research is that this is the research flow. I have a sandstone rock samples. And why sandstone? Because sandstone are very good candidate to store CO2 because they have a lot of permeability, natural permeability. So they are a good candidate. We have these samples. We collect images. First, we cut a thin slice, what is called the thin section, very thin slice, and we collect images. And then from this rock, from these images, we collect two kinds of images. What is important to know is that these two images are complementary, give us complementary information that allow us to have unique information on a rock. By the combination of these two images, we can estimate the cementation and other properties. And then we apply the same procedure we saw before with the bicycle, the segmentation, dividing an images into different components we are interested in. Which are, these components are minerals, so less intriguing than bike, cars, but this is our field, and this is, for example, quartz cement, porosity, and whatever. And for example, for my case, what we are interested in is the cement. So with this approach, we can automatically find the cementation in a rock, and then use this tool for to answer other scientific questions. For example, which is the relationship between the patterns that we see in this cementation and the permeability and the rock strength. So we can use it as a starting point to answer other scientific questions. So finally, basically, to go back to the bigger picture, the goal of my research is to link earth science, artificial intelligence to give a contribution to combat climate change. So thank you.
Thank you. My name is Eduardo from the Tel Aviv University. I was wondering if you have to do any kind of analysis of what else is around this rock. Like, would it be the risk, for example, that the CO2 would contaminate and acidify some water sources or cause any kind of damage to any life living around this rock?
Yes, you have to do, thank you for the question. And you have to do plenty of analysis. I'm focusing only on the rock properties, but before you have to do assessment of all the fluid path you can have. So you have to have a good estimation of where the CO2 will be after. For example, if you have an aquifer, you have to be sure that the CO2 is not going to an aquifer. So basically, in reality, you want the rocks where you pump the CO2 to be super permeable, but then you want for the rock surrounding the hosting rock to be not permeable in order to be sure that you won't have leakage of CO2. So you need to study, and to answer your question, you need to know the permeability. It's really important. Permeability is what tells you where the fluid is going, and so you can predict if it's going to intercept aquifer water or is going back to the ground. And so it's important to try to estimate permeability in a faster way.
Hi, I'm Jan from Tel Aviv University. I have a question on this image, or to the technique which is depicted by this image. You put gas into the earth, right? So you put CO2 gas. Under which state is the CO2? Is it gas? Because in which case it's a lot of volume to bury in the ground.
Yeah, it's pressured. Yeah, it's pressured, but it's gas. It's a high pressure gas.
How much volume can you pressure to the ground?
No, honestly, I'm not an expert of this kind of. I'm more into the geology part. This is more engineering. I don't know. I could create a number, but I won't.
Hi, Rolando. Patricia from the Technion. Actually, I wanted to ask you first of all, great talk. And the amount of CO2 in the environment that you are kind of trying to trapped in the rocks is going to affect the levels of CO2. It's going to affect the capacity of cementation of the rocks, of the sand, in this case of the sand rocks.
The what?
Yeah, sorry. The amount of CO2 that you would find in the environment. In this case, you are showing here that you are doing this technique close to a factory that is releasing higher amount of CO2. So my question is if you know, maybe you don't know it, but if the amounts of CO2 are going to affect the capacity of cementation of the sand rock that you're analyzing.
I don't understand. What do you mean the capacity of cementation? Or what do you mean with the capacity of cementation?
So the way the sand is becoming cemented and creating the rock.
No, that's not going to affect because these are already cemented rocks. So these are already rocks. And of course, you need to study which kind of rocks you have because there could be chemical reaction with the CO2. So you need to know in advance if something is going to change. So you need to do this. But these are already rocks. You're already storing in rocks. So in the fracture of rocks, natural pores and fracture of rock. But you need to know if there could be some reaction. So it depends on the rocks. There are a lot of studies, of feasibility studies before. Okay. And just to add, this usually the main goal of this CO2 storage is to make some industry which is really heavy in CO2 production to be more sustainable because there are some industry that can't really become CO2 free. One is cement, for example. So the idea is in this way you can be more sustainable even for the worst industry that we still need, like steel and some other stuff.
Okay. Thank you very much.
Thank you, Ronaldo. Herman from Hebrew University. Since we know that there are different structure of soil. You use image to train your EA. Why don't you add also chemical reaction, physical characteristic to improve the potential of your EA?
No, thank you for the question. Yeah, of course we can. The more the data, the better could be the prediction. This is the data set we have. Basically, where the parameters that are more going to influence cementation and permeability are the. Now let's go back to this slide. Are the distribution of the more than chemical parameter? What is this is a mechanical thing. Cementation is a mechanical thing. So honestly, I won't expect the chemical composition to influence cementation and the permeability. Probably what it really influences from a geological point of view is the chemical condition where cementation happened, but millions of years ago. So that could be an information to you to know, because that can influence. You have the same rock, but if the chemical condition where they formed was different, you can have a very different level of cementation. But the pure chemical composition of a rock is not going to be really, in my opinion, really important to determine the cementation of a rock. It's more.
Hi, Flavio from Hebrew University. You could have shown pictures too of the flooding of right now.
Yeah, also now there is in Italy in the same area.
Veramente un disastro, diluvio. So my question is this: did I understand it correctly that now you're taking slices of the soil or of these stones and analyze it, and then you teach? You give basically information. You say, look, this is what it looks like to me as a trained geologist, and you teach AI to, in a way, with time, abstract or like understand this by itself. Is that right?
Yeah, exactly. So there is a first stage where I tell to the machine which is the correct answer.
How many do you have to do of those?
I already did 60,
wow.
And with the image, and that was a really painful stage because you have to go. So the idea is to waste time one time to not have to waste time in the future. So basically, I have to create some images like this, which is the truth based on my experience, other colleagues' experience. And then I use that as a ground truth to train the algorithm. So the algorithm has to learn. And so, yeah, we are planning to expand, of course, the data set, but that's the most
really
time-consuming part of the...
Epistemologically speaking, I see a connection between the previous talk and this talk, in the sense that, and you know, as a scientist or as whatever we're doing here, the dealing with a tremendous amount of facts and details, and coming up with abstractions, like theories or worldviews or genealogies or whatever we want to call it. This movement seems to be really central to both of you guys. So, in a way, you're creating the conspiracy theory. You know, like you're training AI to come up with the conspiracy theory of high cementation.
Yeah,
that's
but
just
that's the problem of thank you. No, that's there is also always a bias in every algorithm because you train to data that I'm feeding. There is my bias inside this data. So the idea is that my bias is less than it's more. I'm trained enough to give enough to create an algorithm enough accurate. It won't be a little bit biased, of course, and that's the principle of. There is nothing really intelligent in artificial intelligence. The principle is garbage in, garbage out. So if I'm biased, will be biased also the algorithm.
Rolando, thank you very much. We're out of time. Thank you.
Thank you.